Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I'm learning quickly, I don't claim any real expertise. Today, we're looking at the 73rd Project Euler problem. As always, I will link to both the problem and my repo in the description. Let's dive in. Problem 73, counting fractions in a range. Consider the fraction n over d where n and d are positive integers. If n less than d and highest common factor of n and d equals 1, it is called a reduced proper fraction. If we list the set of reduced proper fractions for d less than or equal to 8 in ascending order of size, we get all this. It can be seen that there are three fractions between 1/3 and 1/2. How many fractions lie between 1/3 and 1/2 in the sorted set of reduced proper fractions for d less than or equal to 12,000? Okay, so this is actually some of the previous couple of problems. But here, we just need to count how many of these values are between these, how many are between these two values. So, I think this one, since our d is less than or equal to 12,000, we can do a very simple solution. So let's go ahead, start our problem 73 file. Okay. So I'm gonna go ahead and steal our from date time stuff. As always. In this case, let's start with limit equal to 8, just to make sure that we get the formula correct. And then here we're going to say num fractions equals 0. And actually, we want to, or at least I think we would need the primes. So I'm going to go ahead and grab our isPrime function as our isPrime logic as well. So this will set us up with an array for all of the prime numbers. And then we don't necessarily just want it to be like that. It'll be easier if we just have the primes in an array. So if we do this, we can do a list comprehension where we do I for I in range limit. No. Yeah, limit plus 1. Where if is prime I. What we can say. And that'll give us a list of all of the prime numbers. So now we can say for let's say for d in range limit plus 1, And then for n in range b, then we are going to test whether n over d is between 1/3 and 1/2. And then test whether is reduced if both increment num fractions. Okay, so our lower bound equals 1 divided by 3, and our upper bound equals 1 divided by 2. So this one, it could potentially give us some problems, depending, but I don't think that it will because our limit is so low. There will be a number as the denominator gets higher and higher and higher, there will be a number that is very, very close to 1 over 3. But I don't think we're quite going to get there. Okay, so we want to say if, or actually we want to do, let's call this fraction equals n over d. And then we are going to say if lower bound is less than fraction is less than upper bound. Because Python lets us do that. And it's a little bit, the first time I saw it, I found it a tiny bit, like, mind-bendy, because we normally don't see patterns like this. But, in this case, it very much makes sense because we want to make sure that the fraction is between but not equal to these two numbers. So what I am going to do here is I am going to say for f in primes, if n mod equals 0 and d mod equals 0, or actually, I'm going to say is reduced equals true. And then if we find one like this, then is reduced equals false. And then here I'm going to also have to say if f is greater than n, then break. Because we don't want to continue looping through all of the primes when they can no longer be a factor for n. So I'm just going to say here, if it is reduced, then num fractions plus equal 1. Now, this is not an efficient way of going about this, in my opinion. As you can see, we have triple inner for loop. But again, because d is less than or equal to 12,000, I don't think that will cause an actual issue. I think we'll be able to do this no problem. Okay, so we found 3 fractions for a limit of 8. Let's just double check real quick, and yes, that is the correct answer for a limit of 8. Let's go ahead for our limit of 12,000. See how long that takes. As I mentioned, this is going to take quite a lot longer. Um, but that's okay. Uh, Depending. It should give us the correct answer, but if it takes longer than a minute, then we have to come up with a more efficient algorithm, right? So, it's looking like it might take longer than a minute. We're going to let it run and see. And in the meanwhile, okay. So, in the previous problem, we ended up counting up how many relative primes there were for a particular number because we know that that's how many um reduced proper fractions there are for a particular denominator. It's the same as the relative primes. But that doesn't quite work for what we're doing here because what we're doing here does require us to have this reduced proper fraction. So let's look back at our previous problem that was similar to this. And in here, what I ended up doing was I built in a thing right here where I sort of started with a lower limit here. And I think that's going to end up being smart to do with our other one. Um, and here, we weren't trying to count the number of fractions, and we did not end up needing to know about whether it was a reduced proper fraction. So I do think I want to have something like this in problem 73 so we don't waste time for things lower than 1/2. So let's see. So here I did start times fraction, but here I would want to do lower bound. And then I would want to have it be start D. And then we don't actually need this check because it will, by definition, be that, I think. Um, but let's go ahead and cancel this out. We'll go ahead and restart it with just that change. And I think that that will not be quite enough, but it'll get us closer. Oh, and we should actually start with 2 here. But that won't make very much difference so far as efficiency goes. Okay, so we don't really want to do quite like this, I don't think, because this is a triple for loop, and those are generally speaking undesirable. um, so let's see here. Another way of doing this would be to find all of the relative primes for every d, and then going through those instead of going through n and then f. So again, it doesn't really matter. Ah, we can also do this, where we have a start and an end, and that'll save us some time since we don't actually care about anything over than 1/2. And we don't want to waste a whole bunch of time looping through numbers we don't care about. So starting it over with that probably won't buy us quite enough time, but it'll be closer. And now this is likely to be true for practically everything in this range, except for maybe the very first and very last numbers. So we don't have to worry so much about this if. And then for testing whether n over d is reduced, it would be better to have a list of the relatively prime numbers, honestly. So, let's see. Let's make an is relative prime equals just d, because, and then is relative prime 0, oops, is always false. And then let's just say for I in range 2 up to half of d plus 1. If it is relative prime and it should not be. Then we set it to false. And then we do our k equals I times 2. And while k is less than d is relatively prime of k also equals false. And increment k by I. Okay, so now we have all of these relative primes sorted. we can then say if is relative prime in and now we don't need to do any of that. Now, this might not look much faster because it's still 3 for loops, but the trick is that now it isn't 3 nested for loops. The for loops are only nested twice. And I'm going to go ahead and take those 2 lines and put them down here. So now maybe we'll be able to do this in our less than a minute time frame. And it saves us a lot of duplicate calculations. Okay, so as we can see, that took less than 10 seconds. Let's see if it's the correct answer. I think it very much will be, but we have to double check these things. All right, there we go. So that is the correct answer, and I think that this is a good lesson for just look how much faster it was once we stopped doing a triple nested for loop. And actually, we can make this go even faster because we no longer need all of this. So now if we run that again, it should take a lot less than 10, or it should take at least somewhat less than 10 seconds. So let's see. Okay, so that dropped it down to about 8 or 9 seconds. So not a significant time saving because it's just a very efficient algorithm for finding primes, but pretty good because we don't want to be doing a bunch of calculations and then throwing them away effectively. All right, so there we go. I'm going to call it there for that one. If you have any questions, feel free to drop a comment below. And if you are struggling with a code challenge and would like my help, check the link in the description and you can schedule a call with me. All right. Catch you in the next one.